İYTE Kuantum Günlerinde Mathematical Origin and Physical Nature of Quantum State başlıklı sunumunu yapmak üzere Profesör Doktor Oktay Pashaev'i sahneye davet ediyorum.
Before starting my talk, I should tell you an important observation related with this event. It is, as noticed, organized by students, and this generally not big event, but in beginning of 20th century, when Max Planck published his paper, first paper on quantum, this paper didn't noticed by people. But as you can see, after 120 years, all this equipment are based on quantum. So this is why I believe that this is beginning maybe of the future, quantum future, which will be developed as technology in this institute also. Then, second observation is following. Quantum days, it's called. Why days are quantum? I was thinking about this, right? Because in fact we are counting, right? Process of counting, it is in fact computation. Then question is, we have any measurement like So when we speak about a quantization of days. In fact, what we did, our students did quantization of days, and I was thinking, okay, you have periodic motion, and periodic motion we have everywhere, starting from the everyday, rotation of Earth, give us measurement of the days, and periodic motion of Earth around in elliptic orbit around the Sun, give us measurement of the year, right? So then we have such type of, let us say, continuous process. For example, 1 year. 1 year is very big, right? Time period, and in one and what happened interesting? We have quantum jumps. Where we have quantum? When we have quantum jumps. Quantum jumps appear when we have New Year. New Year, in fact, appear in, let us say, depends on your clock, what you are using, right? Because when you have, why it is so important events, right? We have declaring that it appear instantly. What means instantly? You should use some clocks, right? Simplest clocks, okay, you are measuring according to the standard watch, for example, but more precise clocks are atomic clocks. In atomic clocks, you are using process inside of atoms. Now, you see, we cannot measure these events, jump smaller than this distance. But then, what happened with Earth? Earth is rotating around the Sun in an elliptic orbit when it is passing to a new circle. Right? It is giving one cycle, the next cycle. Transition to the new cycle implies also that you have this small distance to pass point, right? One point becomes 2 points when you put some point on the continuous trajectory. So in this case, what you can see, this jump transition is related with small distance. What is the smallest distance? It is atomic size. Then what we have? We have that at atomic scale, we have smallest distance and smallest time. So these two correspond that you have smallest oscillating process in atoms, right? Of course, if you try classical model of electron in atom, electron is moving along elliptic orbit around the nucleons, but then you will have the same problem, right? Because then you need again to look smaller if in this trajectory again point, and then again repeating the same situation like in this motion of the Earth. But it's impossible because it is atom. It means at atomic level something drastically changed. You cannot measure process with exact precision in time and in space. Okay, after this, let me start my talk. No, ben yapmayacağım. Okay. Okay, so first, let me start from the following observation. So I will start from the more general, let us say, observation, and I follow in my presentation three main, let us say, ideas. One idea is that it is what Enrico Fermi, when he wrote an article for Encyclopedia, he told that first few sentences everyone should understand. After this, you can write everything what you like. Second one is related with simplicity. I will try to do everything simple, but not simple. And the third one, if I have very complicated concepts or formulas, I will replace them by pictures. Okay? These are three things. And I will start from the Schrödinger, which he wrote article, which is called 2,400 Years of Quantum Theory. In this article, he discussed that basic ideas which we are using in quantum theory discovered long time ago. And the father of atomic theory in Western should be considered as Leftipus, from Miletus, which is very close here, which I should notice, but not much information about Leftipus we know. His pupil Democritus, the atomic theory of Democritus, which is known in ancient Greek, and then in Roman period Epicurus worked on this, and Lucretius. Lucretius wrote the poem on nature of things, from which we learn that atoms, if you like to describe world made from atoms, you should imply that atoms are not deterministically moving particles, something like this, because they should include some type of spontaneous motion or free will. This is why he discussed atoms with free will. Newton, when he considered his theory of light, you know the theory of light, it is one of the real physical theory in which we have two particle and wave description depending on period of time. Let us say Newton discussed light as a set of particles. So it is also before theory of photons by Einstein. And important is when this type of light coming to the sun media, optical media. In this case, problem is some part of the light is transferring, some part is reflecting. So from point of view of particle, what particle is doing? To reflect or to go further? So this light introduced theory of Higgs. Higgs, in modern time, we should call it as a quantum mechanical jumps. So historically appear, let us say, ideas that if you have atomic theory, then you should imply some type of jumps, quantum mechanical jumps. Then we can ask why these people didn't discover quantum theory. Because we know that they used, so this is first picture, this one, you see, it is from the prehistoric period, caves. So counting already known from prehistoric time. This is ancient Greek proportion, golden ratio, and others. So why they didn't discover quantum theory? So answer to this question, trying to answer to this question, we are coming to the problem that in fact the mathematics was not sufficient. The mathematics of ancient time was sufficiently primitive compared with modern mathematics. So 2,000 years we need to develop high level of mathematics to be able to describe quantum phenomena at such level that we can produce technology based on quantum. So since mathematics is so important, so let us try to understand why it is so important. Very important. So there is a book of Oswald Spengler, Decline of the West, very famous book. In this book, he started the book French about the decline of the civilization, he started from analyzing of the concept of numbers. And he told that concept of number deeply hidden in the basis of any culture. So, doğar hesaplamalı olan bir şey. This is just follow that nature is countable. This is big paradox. So you see Galileo writing nature written on the language of mathematics, or Wigner wrote unreasonable effectiveness of mathematics in natural science. And according to this, if we look to ancient culture, we notice that it is based on natural numbers and proportions. I will call some names, but you should understand that these names, when we keep, it is just symbols. Because real historical, let us say, who discovered it and what discovered it, then very complicated subject. It is also some uncertainty relation can be used. So next level, it is Western culture, enlightenment, which is Newton and Leibniz. Then appear real numbers, functions, and calculus, what is called, right? And if we look for the modern time, so what happened in 120 years? We developed new type of calculus, which is symbolic calculus, of which is cube number, so-called, which is non-commutative number. So these are one of the properties. I will tell about it a little bit. But let me tell you why concept of nature is hidden inside of the culture. So for modern people, we didn't notice this, but we know this because all of us are digital slaves, right? Every day we are spending many hours in virtual world. What we are doing, we are communicating by number 0101, right? So watching video, music, listening, or filling some form, RTS or something else, right? So number deeply involved in our society also. Since we are speaking about quantum, so we should understand what kind of number requires quantum. So let me briefly say evolution of numbers first for description of so-called quantum state. So natural numbers according to Peano was given by God. All other made from humans. Okay? Then if you see ratio to rational number, it is proportion. Proportion, it is according to ancient doctrine, it is properties belonging to composite object. In composite object, you have proportion, and proportion shows the beauty. So if you have golden ratio proportion, for example, it is the concept of beauty. Then appear real numbers. Symbolically, I am writing Leibniz, but of course we understand the square root of 2 was known much more before. So square root of 2, p and others. These are real numbers. Then concept of numbers become more complicated, complex number. It is Cardano, one of the person who invented not only Cardan for the car, mechanical, but also complex numbers and also probability. This is why he make a article, there is a relation, he analyzing that Cardano developed, he developed complex numbers, invented, then he worked in probability, and his life was very stochastic. So this was very quantum. Next level is quaternions. Generalizing complex numbers, Hamilton introduced quaternions. And quaternions' first important observation was non-commutative object. This why, in fact, he didn't understand that these quaternions can be applied in quantum physics. This is very interesting because quaternions become description of spin of electrons. But in mechanical engineering, people use quaternion to describe motion of rigid body. Then octonions appear number. Octonions are non-associative numbers. People discussing application in string theory and other stuff, but these are, let us say, part which is in discussion. Surreal numbers exist also, and we don't know when it will finish, this development. But then, if you look real numbers, you have vector in one dimension. If you have 3 real number, x, y, z, then it becomes vector in 3 dimensions. Then you can extend it for n dimension. You have n real number, x1, xn. Then you can go further considering m going to infinity, then you have vector with countable infinite number of dimensions. Then to have length finite for this vector, you should impose a condition, this one, right? That total sum, this is, let us say, total sum should be less than infinity. This you can formulate as a sum Pythagoras theorem, but infinite dimension. So this is just to show how far from Pythagoras we move, right? Because Pythagoras considered just in the plane, but this is in infinite dimensions. And even it could be non-countable infinite number. In this case, you should consider function as a vector, and integral, square integrable function determine space, which is Hilbert space. And this is in fact space in which living quantum system. So just make it in a more abstract way. Paul Dirac, one of the creators of the quantum mechanics, introduced abstract concept of the vector, which is called characterizing quantum state. So this is one part of the story about quantum state. Next one is related with matrices and operators. This is second part. So two vectors, if you multiply, then you have object which you can call as a tensors. Tensors in physics, one of the first to introduce was Einstein. He worked with tensors to general theory relativity to create. So you have metric tensor, curvature tensor. Then tensors with two indices you can consider as a matrix, n by n matrix. So it was Heisenberg and Born introducing physics. When Heisenberg wrote his first paper on in quantum mechanics, he multiplied matrices, but he didn't know that these are matrices. For modern students, of course, it is strange because every modern student knows what is the, especially from EYTE, know what is the matrix, right? Heisenberg didn't know this, but he wrote great paper. Max Born, his teacher, was more educated in mathematics, and he remembered that some before used such type of object with such a rule of multiplication, which is called matrices. Then it was great discovery. Matrix is important. Okay? Then from the matrices, important one are Hermitian matrices, because for these matrices you have real eigenvalues. This way they can be applied for the physical system. And then when Max Born visited MIT, he discussed with Norbert Wiener, you know maybe his book about mathematics. I am a mathematician, it's called. He wrote several popular books, and they found that the general symbolical representation of matrix are operators. Operators which are, because matrix acts in one to another one. So operators. Operators, for example, here is simplest operator for momentum. So this operator should be Hermitian. In this case, we have concept of quantum observables. These quantum observables, what are conditioned in addition to be Hermitian, are linear operators. So they should act on the superposition of two states. On superposition of two states, this one, right, in this form. And this is generally known a long time ago for many linear differential equations we can formulate in terms of linear operator. And important here is the so-called concept of superposition of quantum state, because now it has become something more important than just adding solution of some differential equations. And what is the second important moment, which is followed also from matrix representation, that matrices are non-commutative. Multiplication of matrices you cannot change. For not every matrix you can commute. So non-commutative, then it appears that operators are also non-commutative, and coordinate momentum operator non-commutative. From this, just using simple mathematical steps, you can discover Heisenberg uncertainty relation. Okay. Then for description of electron, charge of electron, it happens that if you like to use wave approach, wave functions, then this wave function should be complex value. So complex wave function appear. For description of spin of electron, I already mentioned it, you need two component spinor wave function and quaternions. So quaternions become useful for description of the spin of the electron, and continuing in this direction, mathematical ideas. Next one is four-component wave function introduced by Dirac for description of relativistic electron. So this is, let us say briefly, of course it is not finished, but I am trying to do it more or less understandable. So this is two concepts, states and observables. And now, why we have such type of strange splitting for states and observables? It happened because we have classical and, so let us compare classical and quantum physics from the point of view of this description of this state. Classical state is described by coordinate and momentum of particle. Classical observable is the same, coordinate momentum. And they're the same, state and observable are the same. So from this follow independence of observation. So you are watching TV, right? You are not entering what is going in your TV, right? So this classical picture, your observation is not influenced the processes. But in quantum physics, it is happening different because quantum state, time, and quantum observable are two different mathematical. Quantum state, it is vector, generally from Hilbert space. Quantum observables are Hermitian operator, generally non-commutative. So state and observable are different. From this follows that your process of observation influences the system at mathematical level. Of course, people think physically first, that if you observe, for example, Apple will not change the property, but if Apple would be at atomic level, observation it is collision with photons, photon will change the state of the atom. Then observation destroys the state of the atom. But it takes time to formulate it in a very simple mathematical form. So that's why we have two basic fundamental quantum principles. First, basic quantum principle, non-commutativity of quantum observables here. And second basic quantum principle, superposition of the state. That state can be superposed. To explain a little bit this type of concept, I used here superposition principle, how it appears, because idea of superposition appeared a long time ago. When we try to combine some property together, appears such type of mythological things, for example, which include human, lion, and eagle wings together as a one, let us say. So this type of property combined together, you can consider as some type of superposition of states, but symbolically, of course. I told that I will put you a picture. And mythology developed different contradictory terms, so which called oxymoron, contradiction in terms. For example, visible, invisible. In mythology, you can see that they describe all possible states. So if we from this move to the superposition principle in quantum physics, there appear also some mythological, let us say, animal which is called Schrödinger cat state. You can see a lot of stuff, videos, books written on the Schrödinger cat state. So this is Erwin Schrödinger, and this is not his cat, but it is cat. You see here states which corresponds to the it is written here Schrödinger cat. It is mortal immortal, superposition of two states. And another type of representation similar to Schrödinger cat state, it is so-called wave particle duality. It means that your wave function can be superposition of two oxymoron, let us say, terms, continuity and discreteness. These are philosophical concepts, discrete and continuity. And this you can combine together because even in formalism, just formalism for continuous discrete spectrum, you can write in the corresponding states. So wave are continuous wave and particles are discrete. And The superposition principle leads to the concept of entanglement, very important fundamental concept. I can talk about this a lot of time. Most famous and most known one, it is relation between Alice and Bob. Relation between Alice and Bob is that Alice and Bob can take two values, 0 and 1, let us call them, right? And then you compose them together. They have some interrelation. Then Alice and Bob move to the big distance, and then Alice decided, not Alice, but you decided to do measurement on this state. When you do measurement on this state, then common state will collapse, or 0 or 1. Okay, Alice can take or 0 or 1, happy, unhappy. What is interesting, according to what is written here, at the same time, Bob, independently where he is, even on the another planets, he should feel the same thing. Otherwise, will be conflict. So it is like in family, right? So this is why Bob should follow in this case to Alice. But of course, you can write another state in opposite. This is just to illustrate entanglement by simple term. And this, to finish this general part, I will tell you that uncertainty relation for quantum operators P and Q imply commutativity of operators produce uncertainty relation. So you have in generally description of momentum and coordinate of particle in so-called phase space. You have phase space PQ for one particle two-dimensional space, and this implies, because delta P to delta Q, it is area of rectangle. As the area of rectangle, it shows that your rectangle could not have area smaller than a Planck constant. Smaller than Planck constant. So this one, if you have phase space, your phase space then splitted. This is called tessellation. For small elements, different kind. I just illustrated this by more vivid picture of tessellation. You can see in many places this tessellation starting from the floor and the church, mosque, and others. So phase space become tessellated. But of course, in such picture, very important, because from classical point of view, boundaries to be the compatible, you should have repeated pattern, for example. But in quantum level, so you cannot ask what happened at the boundary. So what is the quantum tessellation? It is just idea of quantization in phase space, what is called. Okay, after this, let me, in fact, tell you some outlines. I briefly tell you some ideas which I was working, and to illustrate you last time, illustrate some relation between mathematical, classical, let us say, mathematical ideas and modern quantum information theory. So I will discuss Apollonius circles, relation with cubic representation, Pythagoras theorem for tetrahedron in 3 dimensions, and entanglement of Euclidean states, then Fibonacci numbers and quantum point flipping, geometric probabilities for qubit space, and quantum kaleidoscope of covariant states. So first, let me start from Apollonius circles and qubit representation. You know that qubit is represented by sphere. As a sphere is like Earth, right? This geometrically, this sphere you cannot map to the plane. Why? Because every time you will have one singular point, it could be North Pole or South Pole, which you cannot draw. This why you can have two options, or have map like this sphere-erase map, in which it is some piece of the Earth, not the full Earth. But if you like to full Earth, you should have two pieces. This is why for atlas, when you have always this type of description. So, and then question is, could we write such type of atlas for qubit state, which is also sphere? This was idea. And Apollonius in Perga also near Antalya, you know, the ancient city of Perga, great mathematician of ancient time. He worked in Alexandria. He wrote famous book, which is called Books on Conic Sections. So conic sections are just intersection of conbound planes. This intersection appears as a curve, hyperbola, parabola, ellipse, and circle. What is important? All these curves are trajectory of motion of planets, meteorites, and others. This was an interesting discovery. And for us, interesting point is following. He made a definition of what is circles. Circle everyone knows, right? It is set of points equidistant from the center, right? It is standard definition, x squared plus y squared equal r squared. But he was non-trivial person. This is why he did another definition. This definition is based not on monotheistic approach, that you have dot in the center and around you have circle, sphere, or something else. But it is dualistic approach. You have two points, let us say A and B, and then you consider distance from these 2 points, not from one center, but from 2 centers. You should take into account from this center. And then you're asking to which one you are more close. What to do? Ratio of distances. Ratio of distances written, fixed. Then you have set of circles. And this set of circles people use, in fact, in electrostatics. So if you have 2 charges, then you are asking what is the equipotential lines between these charges. This equipotential line exactly becomes a Apollonian circle. This is a set of circles. Okay. So why it is convenient for us? Because when you discuss unit of quantum information, this more or less now everyone knows that this is sphere. North pole is 0 state, south pole is 1 state, and generic any point on this sphere describes a state of Q. Then, in this representation, it is nice, but it's required always work with sphere. If you like to have some geometrical calculations, you need to have map of it, so atlas. So you cannot just project, because if you project one of the points, it's stereographic projection, one of the points going to infinity. But Apollonius representation allows you to write it in this form. So this is Apollonius map of one qubit state. So you see, you have 0 state, 1 state here, and this is the point. So if you look for the distance between them, these distances, ratio of distances is ratio of probabilities. So probability of given state to jump to 0 or to the 1, ratio is fixed. Okay? Then this can be generalized for 2 qubit states. For this, we should take CNOT gate. This gate introducing entanglement for direct product Apollonius state is 0 state. Then we get 2 qubit Apollonius state, which is written here. And then you calculate entanglement characteristic by number, which is called concurrent. Okay. By this number, then you have again set of Apollonius circles, which is a map of 2 qubit state. And now entanglement is constant along this circle. So this is plays a role like potential in electrostatics. Concurrents play a role of the potential. Okay. This is this map, and this is picture just for contour plot. We can call it geographical 2D map, and these are physical 3D map. This is just Apollonius, and next short subject is Pythagoras theorem in 3 dimensions, which is called Big Y theorem, but there is many people who work on this. But okay, just to say difference from Pythagoras, Big Y theorem for tetrahedron and entanglement of Q3 state. This is Pythagoras theorem. So what is important? It is theorem on the areas, right? Addition of areas of these squares. And in 3 dimension, generalization of this Pythagoras theorem is following. You have a tetrahedron, right tetrahedron. It is like corner exit room, right? And then if you add now not side but square of areas, 3 areas, square areas, it gives you square of this area. So this is 3-dimensional Pythagoras theorem. This is pure mathematical subject which is not related with any type of quantum information from the beginning. But I will show that this exactly related with properties of entanglement of two states. For this, I will briefly use some, let us say, notation from the information theory. So I will consider if you have two qubit states, you have this type of basis 0, 0, 0, 1, 1, 0, 1, 1, and normalization condition. We can rewrite this state as a combination of two one-qubit states, P and Xi, and then everything depends, entanglement properties. These states are linearly independent or independent. If they're linearly independent, then you have entangled state. If dependent, then these states are separable. But we know geometrically, so if you have two vectors in plane, then these vectors are linearly dependent if they're on the same line. But if they're not on the same line, they have some angle, you have them area between them. You have a parallelogram, and the area of parallelogram can be considered as a measure of linearly dependence. Okay? This was idea of entanglement related with area, but area is, you can write as a vector product or as determinant form, right? From components of vector. This way we are coming, if we calculate this area, that concurrence characteristic of entanglement taking value between 0 and 1, when it is 0, states are separable, when it is 1, maximally entangled. This characteristic is double area. We have, we see a relation between entanglement and area. This is interesting because this type of property appears when you have black hole physics. In black hole physics, you have, for example, Schwarzschild black hole, you have even horizon, which is sphere. And then area of this sphere measure entropy of the black hole. So this is why entanglement property, this property of entropy, is related with area. Geometrically as an area characteristic. This can be written, let me not concentrate on the full stuff because it requires lectures. So we can calculate some type of Pythagoras theorem relating concurrence with the so-called density matrix, reduced density matrix. And in this theorem, if trace rho R square is equal to 1, concurrent 0, states are separable. If not, then entangled. But entanglement is concurrent. You can ask what is this? One of the options is, as I explained, you can introduce by this Pythagoras type formula. But it is connected with standard definition of entanglement. If you have density matrix, then you calculate so-called von Neumann entropy. Von Neumann entropy, then if you have bipartite system, you take trace, you have reduced density matrix, you calculate von Neumann entropy for reduced density matrix. Then, depending on this entropy, you decide state mixed or not mixed. So, all both, even separated, if state is mixed, reduced, then the state is entangled. And this is the relation between entanglement and the concurrence written in this form. Of course, this formula, in a simple case, when you have just two states, 0 and 1, bipartite system, this formula shows that von Neumann entropy much more complicated object to calculate than the concurrent. This is why concurrent geometrically more easy to do. And if we try to the same stuff to do for two Q-treat states, in Q-treat states, what you have now, Alice admit not 2 but 3 values, 0, 1, 2. This is like when you do calculation of numbers, not in binary system, but system with base 3. Okay, then this is called Q-treat states. So this is basis the composition of Q-treat state. You see number of states increasing, and then concurrents appear in this form. This form, of course, looks, if first time if you look, so it's very complicated. But you can see some symmetries in this expression. And what is it? So I was trying, when I calculated this form, I was trying to understand the meaning of this expression. The meaning of this expression is interesting because you see 2 by 2 matrices, the determinant of 2 by 2 matrices. So this suggests that you have here square of the areas. Square of the areas combining all together. And in fact, it was correct because according to this formula, I have this concurrence in the form of this sum of these squares of the determinants. And for Q3 states, then I decompose it in terms of three 1Q3 states. Then I have vectors, but now vectors define it in the states, not like in qubit and clay. So since in space, we calculate areas of between three vectors. Three vectors in space, these are corresponding areas. Corresponding areas satisfy these formulas. Then, if you calculate maximally entangled state, then vector should be orthogonal. So, as an orthogonal vector, then you have this type of relation. And this relation is exactly become, let me move a little bit forward just to save time. Yes, in this form, so this becomes just the Bigot theorem for tetrahedron. So what happened, let me show here, we have three vectors corresponding to my Q3 state. And then this area describe me entanglement of these two Q3 states. If this area is zero, states are separable. If it is non-zero, then states are entangled. So we have pure, again, geometrical description of these states, symbolically represented here. So you have two objects like two sphinx, which are Q3s, and this is Alice Sphinx, Bob Sphinx relation between them. So entanglement of these states was calculated. Of course, a question could be, can we generalize this concept for two-digit state with arbitrary gauge, for example, 10, 5, or others? Yes, we can, but then we can play with higher dimension, and this is good research problem for mathematics and physics students. Describe entanglement in terms of this type of Pythagoras theorem in multi-dimensions. Okay? I have seen 5 minutes. This one I briefly tell other subject. It is Fibonacci numbers and quantum coin flipping problem. This problem is related with following observation. Every day we are reading about artificial intelligence. People are afraid of artificial intelligence, right? Because they need us. And they think that, okay, we should have something which is different, so which cannot be done by artificial intelligence. These are working usually on algorithms. So this is why we should create some quantum type of algorithms. Maybe they cannot follow, then we would be exceptional. And this is why people start to use work with so-called quantum games, or games including quantum phenomena. This is video from the YouTube. Some video popularizing like discussion this game played with Hawking. So quantum chess, quantum coin become important subject. And so I will relate this with some classical concept, Fibonacci number. Briefly, I will show how Fibonacci number appears in the problem of flipping of quantum coin. So Fibonacci number, everyone knows, it is, many phenomena described by Fibonacci formula, and they're related with so-called golden ratio proportion. And I will discuss problem which was posed in the 18th century by Abraham de Moivre. And problem is find probability of n tossing coin until two consecutive heads appear. So you toss your coin, but at the end, only HH should happen, head, two. So then you count probability. To count such probability, you need to count number of configuration. Okay? So then we have random. So this is random process. Coin is a random variable, and for this random variable, you have characteristic of randomness. Characteristic of randomness you can write in terms of the Shannon entropy. Maximal value of Shannon entropy. Your states are maximally random. It means that all of probabilities are equal. Can be proved. Okay. Similar stuff we can do for quantum state. If you have quantum state which is extended in the basis x1, xm, then jumping to these states characterized by probabilities, you can write it in terms of amplitude of transitions. Then you can characterize the randomness of the state by Shannon entropy. And if you look now, one qubit state, maximally random state, this would be form of this state. So you have 1/2 probabilities to jump this state to 0 or to 1. On Bloch sphere, it is just a quarter of the Bloch sphere. So this can be considered as a quantum coin, which is fair quantum coin. Right? This is how it can be generated by using X gate and then Hadamard gate. Okay. Universality just shows that you can, for n-qubit state, you can reduce it by one measurement to the next n-1 state, and then recursively you can reduce the number of qubits. And then we are coming to the problem following. Find probability of measurement quantum coin states in n trials. Repeated pattern of the state 1 only in the last 2 final measurements will appear. So it means I'm counting this state when you have 1, 1 at the end. So I need to count all possible configuration here. But it means that I have now multiple qubit states. So this multiple qubit state, I am counting how many states I have that 1, 1 at the end. So it is two combinatorial problem. And this is related to Fibonacci number, to Fibonacci itself. Fibonacci works with adult and baby rabbits. So you have restriction because baby become adult survive, is not dying, and keep producing one baby. Baby after 1 month become again adult, producing so baby, and then adult is not dying, so number is increasing. So it becomes Fibonacci number. So I have now similar tree, Fibonacci tree for quantum states. Here. So last one are 1, 1. Then I have 0. So I should not have repeated 1, 1 states here. So this way, after 1, only 0 can appear. Right? In the Fibonacci, I have restriction. Okay? From 0, I can have 0 or 1, it's okay. Then I have set of interesting numbers corresponding to this Fibonacci tree. And if I count number of these states, then this number of states is Fibonacci number. And probability, to calculate probability, Fibonacci number for every flipping I have 1/2, 1/2 power n. So this becomes a probability written for the coin, this measurement problem. Then generating function we can write. What is interesting here is that in this problem, you should consider qubit state with infinite number, multiple, with ongoing to infinity. This is interesting because, you know, in realistic quantum computation, we need millions and millions qubits. In this case, big number n is required, so we should have some theory for big number of qubits. These are just some formulas. This is interesting. Golden ratio how appeared here, because if you take states with n qubit and n plus 1 qubit, then ratio to Fibonacci numbers in the limit give you golden ratio. So golden ratio appears in description of probabilities or number of states for this coin flipping problem. This can be generalized, and this I will skip but I will just show you formulas because they're beautiful. You have bipartite system, you have then product of Fibonacci numbers. Tripartite system, you have 3 Fibonacci number product with, then multipartite system, you have this type of products of Fibonacci number. So this is just how Fibonacci number appear in description of these quantum coins. And then we are coming, then this type of states, which is now it is a qubit state, maximally random qubit state. And then I should discuss 2 simple problems. One is problem is geometric probabilities. Geometric probability is dark, what you play by Monte Carlo method. It means you are sending that randomly, right, point inside, then you count number of points inside and outside. Ratio give you probability, ratio of 2 areas. Okay, this is problem of Buffon problem I will skip. I will tell that first geometric probability on qubit appear. If you look for the probability of jumping to the to P1, probability jumping to one state, you can define it as geometrically as a ratio of red area to the sphere area. So it becomes geometric probability. And another one for n qubit states, let me show the picture. So you can consider random n-qubit state, then if you like to count probabilities for big number n, then it could be geometrical ratio of these lengths to the total lengths, right? Because number is characterizing lengths. You can generalize it for bipartite system. Then you have geometrical probability as a ratio of areas of these squares or cube in multidimensional case and multidimensional cubes. And last one, it is just also a few slides, quantum kaleidoscope. Everyone knows what is a kaleidoscope. And this type of kaleidoscope can be discussed for the so-called coherent state of light. Coherent state of light is a state of many photons. This is why they are more classical. We can see light according to this in laser, this one, for example. So you have infinite number of photons in such state. Problem is that state not orthogonal. This is why people created so-called cat state. It is addition and subtraction of alpha minus alpha states and entanglement properties. And these are cat states. They appear from this coherent state if you split them for even odd states. Even odd in this summation. Summation to all positive integer n, you split for the even odd numbers. You get two cat states describing this, let us say, photonic cat states, let us say. Then, if you look for the, you can of course split two numbers which is divisible for 3. In this case, you have 3 different projection operators and arbitrary state decomposed in 3, 1. Then you have this type of quantum Fourier transformation, and we get then 3 macroscopic states, coherent states, which are orthogonal. This type of states, in fact, discovered experimentally. You can see in Wikipedia is written about this experimental part. So it means that you can consider this as a unit of quantum information, but now these 3 states. So your cat now not dead and alive, but it can three positions. You can go to some mystical writings about such subject, what is it between death and life, just symbolically, or it could be like in Sphinx, you have just 3 basis states. This can be extended to kaleidoscope design states, and let me in last minutes tell you following. This is the cat state represented by reflection principle. So you have cat and reflection of cat. If you take 2 combination, even odd combination, you will get cat states, what is called. Then you can represent them in such type of not so beautiful mathematical form of hydrodynamic flow related with cat state. This is last what I was working on at the moment. It is related with hydrodynamic representation of the quantum state using complex analysis, reflection principle and quantum information, and I'm working at supersymmetric qubit state. But I'd like to finish my talk with following slide. So this is Albert Einstein, who told that God does not play the dice, right? But this is picture of Shiva with his wife Parvati playing dice. So these are 2, let us see, oxymoron states. So, and according to what I presented, God not only played dice and coins, but enjoyed Fibonacci numbers and gold. Okay, so I finish on this. Thank you very much for your attention. Yes.
You mentioned about the Q number spectrum.
Q number is the sense of Dirac. This is quantum number, it means operator. It means operator. But Q number is related with Q calculus, it is different. You mean Q number in the sense of the Q calculus. This is extension of the calculus standard by new definition of number. Number become now function of some parameter Q. So this is different. This requires another talk. So, but this, especially from young people, would like to have some questions, any type of question. So question cannot be stupid, answer could be stupid. So I cannot Pashaev. Yes.
You mentioned about the description.
Sorry?
You mentioned about the description of the space.
Yes. Yes.
Why don't we interact with no?
Approach to the quantization in phase space is quite not too much traditional, but half traditional, let us say. There is some books written, quantization in phase space. Geometry of the phase space, in this case, let us say this way. In classical physics, when you have phase space, you are interested, this phase space, it is sphere, it is torus, or it is plane. Depending on this, your physical system behaves differently. Or it is integrable Cold system because you have infinite number of integrals of motion, or it is some stochastic system. So everything depends on the structure of the phase space. Now, from another side, quantum theory, you should, to construct statistical quantum theory, you need to split phase space for the some elements and then put the same probability to every piece of this phase space. About nodes, I don't know. I mean, it is just maybe you should specify in which context. So nodes in phase space, you like intersections to consider. As I told you, from my opinion, if you like to have a picture, nodes difficult to interpret because picture is beautiful, right? Picture you have polygons putting as a tessellation, but you should understand that boundary of polygons it is not defined, right? Because you are uncertainty relation you have. So this is why it is quantum system. By the way, it is interesting why it is quantum tessellation. Because, for example, to cover this floor, you need squares, right? But boundary should be the same because no Bosch-Loop, right, between them should be. But if you go to quantum theory, in quantum theory, Bosch-Loop, it is not fixed, right, because it is uncertain. From this point of view, tessellation probably is not fixed by specific figures in this case. This is an interesting question, but I don't think that I can say more about this. Other questions? Yes.
Speak about the quantum computation in the light of the vacuum breakdown.
Quantum computation, okay. Important point is that you replace standard unit of information 0,1 by quantum state 0,1. And important is, as I mentioned, one of the basic principles of quantum theory, if 0 and 1 are always quantum state, any superposition of this state is also quantum state. Then it means that if you manipulate by this state, one state, you see that sphere contains infinite number of points, right? From this point of view, information contents of the sphere infinitely bigger than just 2 points, right? Because 2 points, it is sphere, but in one dimension, right? You have 2 equidistant points from origin. But sphere is the 2-dimensional surface, equidistant points from the origin. So this is why you have much bigger information contents. Then if you do computation with this type of states, of course, they're much more contains information, but problem is measurement at the end point. No one would like to discuss this question, but this is fundamental question. Because, okay, you apply gates, you get some computation part, but finally you should distribute to measure, to get numbers. Otherwise you will not get number. You should get 0, 1, 1, 0. Then you have calculation. But this process is probabilistic. You know? So from this point of view, so you should prepare, let us say, briefly, infinite number of these computers at the same state to make this computation. This is why people start this many world interpretation of quantum mechanics. So then everything becomes like deterministic, but in this huge dimensional space. So this is why quantum computation, it is, by the way, why quantum computation is so important, let me tell you, and what was the Feynman idea from the beginning. You know the Moore law, right, that we need smaller and smaller chips, right, to have putting to increase the power of your computer. But when you do miniaturization, so it is not like in calculus. You cannot scale up to a point, right? So it means that you have some limits. Limits coming from Heisenberg uncertainty relation, right? You cannot do smaller than atoms. right? But if you go to atoms, chips made from atoms, in this case, you should use quantum laws because chips not follow the classical laws. Then you should use quantum mechanics. Then appear ideas of a computer which use law of quantum mechanics would be quantum computer. And at the beginning, people didn't know what it is. So this was discussion for a long time. Mathematicians like Manuel made contribution to this. At the moment, it's become very famous, but problems still are too big. Of course, many money is flowing in this direction. This is why many groups interested in this, and especially doing reclam for this. Okay? But we believe that since all this impossible to predict 120 years ago when Planck wrote his article, he was even don't like his article, and people didn't know about his article. But you see results. This is why we cannot predict after 120 years what will happen. So life will change drastically, I think. Because quantum physics, let me tell, the most attractive part of quantum physics, it is magic. And this is for me most attractive part of it. It is magic. It is mathematics, but magical mathematics. Magical physics. So this is why we cannot predict what will be in the future, but could be that world will be completely magician. So we will transport not, so for example, people going to another planet by rockets, right? Or sending satellites and other. Instead of this, we transport quantum states. In this case, any distance would be okay. So we can maybe visit all the universe just transporting our quantum states. So you see, so you would be the same person, but your state would be transported. You will have feeling that you visited everywhere, like if you're watching TV, travel guide or something programs, right? Visiting different countries. I don't know if I answered at least partially because it is could be continued. Other questions?
Can I?
Yes, of course.
Can we still look for quantum advantage conversational side?
Okay, this is yes. This is big competition between big companies that can be beat classical computation. You know that all our bank accounts are related with simple Shor algorithm, factorization algorithm of the numbers. Because if you have huge number, then you should see how you can factorize it. So this requires time, which is usually exponential time. But Shor introduced algorithm, quantum algorithm. Then you can this can be studied in the courses of the quantum computation. This algorithm, so it gives you polynomial time. It means that people expect that with this algorithm you can, I mean, all your accounts will be not secure anymore. So now people are creating new algorithms, and I think for young people who are interested in the quantum algorithms, main problem is following. To do quantum algorithms, quantum computation, you should know basic rules of quantum mechanics. This becomes a big problem because now you know many centers opening, many research groups working in this field, but they need people who knows from one side quantum physics, from another side mathematics, computer science and others, to combine them together. And this is most difficult part, and I hope that this type of events increase what is called quantum culture in this direction. I don't know if I answered your question. This is why every day when you open Google sending different kind of messages, which are basically physicists discovered or quantum computer, become better than classical one at some level, and opposite. Classical computers still are very good. So this part is, I mean, change every day. So jumping every day. This is why to have some, let us say, result to communicate, we should wait some time to see. So it is in progress. In progress. Yes, other questions? Bitti mi? Teşekkür ederim. Çok sağ olun. Thank you very much.